Did he go to the city?
I didn't think so. He didn't tell me.
No, Gary and Elsie went to the job fair.
Yeah.
But
I didn't think Michael was going. I know Skylar wasn't because he was like. I think he's pretending.
what?
Okay, so good afternoon. Welcome to Chemistry Senior Seminar. For those of you in 4901, I think there'll be an outside speaker opportunity on Thursday. I just got the email about a psych professor coming to give a talk Thursday. I didn't get that up on Moodle yet, but that's forthcoming. And I think those are all my announcements. Announcements from the crowd. Anything Chem Club-ish going on, or just trying to survive the last 2.5 weeks? 3.5 weeks, sorry. 3.5 weeks. What's that?
We're that far in?
Yeah. Next week's Thanksgiving, and there's only 2 weeks after that.
What? I keep forgetting.
This 5 months ago is the halfway through finals meeting.
Yeah, sorry. We're closing in on the end. I hate to be the one to report it to you, so I don't know if that's good news or bad news. But we are rapidly approaching the end of the semester. So that wasn't really an announcement, but okay. Might have been your PSA of the day, public service announcement there. Other announcements, questions, concerns? If not, then we need an introduction.
All right, hi everybody, welcome to seminar. Before I introduce today's speaker, I want to introduce or invite all of you to my seminar next week, same time, same place, and I'm going to be presenting on a new drug, an antidepressant using indazoles. But today, Kevin is going to be presenting pressure effects of superconductivity. Kevin is from the Twin Cities. And in his free time, he tutors P-Chem students and likes to hang out with his friends. He is a chemistry and French double major, and after graduating here at Morris, he plans on taking a year and going to France. So without further ado, here's Kevin.
Thank you all. I'm Kevin. Thank you for the lovely introduction. My title is Pressure Effects on Superconductivity. So my research that I did was knowing that superconductivity is a phase change. How does pressure affect this phase change? So I've partitioned out my senior seminar into 4 parts: introduction to superconductivity, the superconducting phase change, and then the heart of my presentation, we have pressure effects on low temperature superconductors, pressure effects on high temperature superconductors. So to know how pressure affects the superconducting phase change, we first have to understand what is superconductivity and what are superconductors. So, superconductors are certain materials that, when cooled below their critical temperature, Tc, they exhibit superconducting properties. Now, when we go past the critical temperature of our material, this is called the superconducting phase change. So our superconducting properties that we get are twofold. One is effectively zero resistance. So in our normal conductors, such as copper wires, copper naturally resists the flow of electrical current. But in our superconductors, we don't get that opposition of force. We get effectively zero resistance. Our other superconducting property is called the Meissner effect. So the Meissner effect is where superconductors reject magnetic fields. So what we have going on here is, on the bottom, we have a superconductor that's being cooled below its critical temperature. On top, we have a magnet. So our superconductor is rejecting the magnetic fields that are created by the magnet, and it can float on top of it, and it can turn a little bit. So now I'm going to get into a little bit of the history of superconductivity. We have 2 major discoveries. Our first is our initial discovery of superconductivity, or the discovery of low temperature superconductors. They were first discovered in 1911 by Professor Onnes. He was a notable Dutch scientist working in the Netherlands at the time. he was conducting experiments on different metals and different elements at really low temperatures and measuring their resistivity. So what he found is that we have mercury at 4.2 Kelvin. And if we cool it 0.01 Kelvin, we get 4.19 Kelvin, we get effectively zero resistance. So this discovery isn't without controversy. Professor Onus notoriously kept a really poor lab notebook. He had terrible handwriting that would rival even my own. And he wrote not on lab notebooks, but on notepads that we use today for our grocery list. Combine those together, right, really poor lab notebooks. Secondly, he had a lab assistant that was known to take many a nap when conducting these experiments. So what's most likely to have happened is that our lab assistant that was conducting experiments and our first discovery of superconductivity, the guy who was conducting the experiments was most likely sleeping. So, all in all, I doubt whether Professor Onus would have passed ITR here, but good for him, he got his Nobel Prize in 1913 for his discovery. So, our next big discovery is our high temperature superconductors. First published in a paper in 1986 by Bendors and Mueller. What they did is they synthesized this inorganic compound, LaBaCuO, and when they have this system, they induce superconductivity. Their critical temperatures blew our initial critical temperatures out of the water at 30 Kelvin. Right? Kelvin is our absolute temperature scale. This opened the door for a vast array of different compounds with different structures, with varying components, with, of course, varying critical temperatures. And further discovery, they won a Nobel Prize in 1987. So I mentioned low temperature superconductors and high temperature superconductors. I'm going to get into what exactly that all means. So our low temperature superconductors are metals, such as lead. This means that they're conductors initially, and their critical temperatures are approximately less than 10 Kelvin or thereabouts. They abide by what's called BCS theory. I'll get to that in a little bit. Our high temperature superconductors are ceramics. These aren't like pottery that I would see at the ceramics class at Morris. They just look like clear plastic. Also been described as like what look like thin layers of tape. They start off as superconductors, and their critical temperatures can range anywhere between 40 Kelvin and 130 Kelvin. Opposite of that, for our low temperature superconductors, there's no universal theory that describes the mechanism of which we get superconductivity. So I mentioned conductors and semiconductors. Since they're different types of conductors, they have fundamentally different band structures. So for our metals, we have an overlap in our valence band or conducting band. And this Fermi level or Fermi energy for metals, this is the highest place where we can have electrons in our valence band, and it overlaps with our conducting band. So we get these electrons in our overlap considered free and can participate in superconductivity. In our semiconductors, however, we have what's called a band gap, or an energy difference between these two. In order to induce conductivity, we do have to promote electrons from our valence band up to our conducting band. Insulators just have larger band gaps. So we have many uses for superconductors. I picked out two of which I find are really interesting. Japan's doing a lot of engineering with these superconductors. They've developed, or they've engineered what are called SE maglev trains, or superconducting magnetic levitation. They're using the Meissner effect. So effectively, these trains are floating, right? And they can reach incredibly high temperatures of somewhere around 373 miles per hour. Another thing they're doing is that in their satellites, where they have X-ray spectrometers, they initially wanted to use copper wires to conduct electricity. However, copper is a good conductor of heat, and it was causing problems in their satellite. So what they did is they took the high temperature superconductor YBCO, a derivative of that was discovered by Bendors and Mueller. These are poor conductors of heat. So it's a perfect match, because we also have a perfect conductor, really poor conductor of heat. So they're really happy with their results. So now we know a little bit more about what superconductors are. Let's get into our superconducting phase change. But first, I have to go over what generally I mean by a phase change. We have a phase change, right, when we're going in between different states of matter. Think solid, liquid, gas. Water is a good example of this. So if I have a glass of water, put it in a freezer, right, I get ice. If I want to make tea, right, I heated up some of the water particles, H2O particles, and I turn it into gas, turn it into vapor. And we're going in between these different phases, right, we get a phase change. So what's interesting, however, is that we get different physical properties for our different phase changes. So if I have a glass water bottle, fill it all the way to the top, cap it, put it in my freezer, what's going to happen? Well, it's going to break. Why is that? This is because solid water has a larger molar volume, so it's going to expand, and our glass is going to break. So we can classify these phase changes based on their physical properties. If all my PChem students, I'm not sure if you're there yet, but my past PChem students, we have a first order, second order classification for phase changes. So let's look at volume right here. This frozen glass water bottle is an example of a first order phase change, where we see a discontinuous function of volume with temperature, because molar volume for ice is greater than that of molar volume for liquid water. A second order phase change is what would happen if we got a continuous function. So we do have these first order, second order classifications for our superconductors, right? But we're dealing with solid state phase transitions, because we're going from one state of matter, or one state of solid to another state of solid, right? We're going from a conductor to a superconductor. So this first order, second order system was initially proposed by these two fellows, Paul Ehrenfest and Lev Landau. Ehrenfest right here, Landau right here. These two guys are really important for our current understanding of science and superconductors, as well as quantum mechanics. So this Paul Ehrenfest guy was really, really good friends with Albert Einstein. This is him and Einstein and Paul Jr., Paul Ehrenfest's son. He was an Austrian physicist working at the time, in the 1930s. And over here we have Lev Landau, who was an important USSR scientist. So what's interesting with these two guys is that within 2 years apart from each other, they both came up with the same classification of superconductors. We have a first order superconducting phase change and a second order superconducting phase change. So what they noticed, and what is true, is that superconductivity is a property of a specific crystal structure. So how are they able to classify them? For our first order phase changes, we would see an abrupt change in our crystal structure. For our second order phase change, we would see a smooth or continuous rearrangement of our crystal lattice in our superconductor. So this was back in the 1930s, so I'm going to go over what we know now. So what we know now is largely due to this guy right here, Yuri Menucha. Hopefully I pronounced that right. This is him right here with his parrot. He's also former USSR, really interesting character. So he got his PhD in Russia, 1950s I think. He worked his way all the way up to be the head of the X-ray crystallography department in the USSR. So he was part of the humanitarian movement in the USSR at the time. So because of this, he was fired from his position. The government had a warrant out for his arrest. So what he did is he moved to the United States and became a research lab assistant at NYU. And when he was there, he worked his way all the way up to become the head research scientist, or one of the head research scientists at the chemistry department. And there he wrote the book on the fundamentals of solid-state phase transitions. So our initial problem, what these two scientists say in the paper Superconducting State Phase Transitions, the problem with the initial classification of second-order phase transitions is that they were hypothetical. There wasn't a good theoretical or experimental basis for this. But we do have now a better technology to assess the crystal structure before after and during our superconducting phase change. So what these two guys did is they took both a theoretical approach and experimental approach, and what they found is that for every single superconducting phase change, we see an abrupt change in our crystal structure of our superconductors before our critical temperature and immediately after our critical temperature. So what they say is that there is enough evidence that second-order superconducting phase transitions do not exist at all, being merely a product of theoretical creativity. This is a big thing, taking down both Lev Landau as well as Paul Ehrenfest. So now we're done with superconductivity and the superconducting phase change. So we're going to get into the heart of my research is how pressure affects this critical temperature. How does pressure affect this superconducting phase change in different superconductors? I start with our low temperature superconductors. So what we know, what theory, I said this before, what theory governs superconductivity in low temperature superconductors is developed by these characters. We have John Bardeen, Leon Cooper, and John R. Schrieffer. They won a Nobel Prize for their theory. Their theory is called BCS, right? BCS. And they got their Nobel Prize in 1956. So before I get into the theory, I'm going to go a little bit into the terminology that I'm going to use. So first up, we have fermions. These are particles such as electrons. They have half integer spin, and they abide by what's called Pauli's exclusion principle. So what Pauli's exclusion principle states is that if we have electrons in our same energy state, they have to have different quantum states, which means one has to spin up, the other one has to be spin down. So what we see right here for F2, our molecular orbital structure, is we have two electrons right here, one spin up and spin down. But since we have more electrons, we have to put the electron into a higher energy state because of Pauli's exclusion principle. Next up, we have bosons. So these are particles such as photons. And you've heard recently about the Higgs boson. This is also a boson. They have integer spin, and they abide by what's called Bose-Einstein statistics, which is different than fermions. So fermions abide by what's called Fermi-Dirac statistics. So the difference between the principles that govern these properties is that our bosons don't have to abide by Pauli's exclusion principle. So we can have multiple different bosons with the same quantum state and the same energy level. This means that we can get a bunch of bosons in really low energy levels. What this means physically is that if we have this ray of light, like my laser pointer right here, we get a coherence in our laser because all these bosons can exist in really small energy levels. That's why we get what's called coherent or continuous light. Next up is our phonon, not to be confused with photon. So phonons are vibrations that result from the crystal lattice. Or phonons are waves that result in the crystal lattice vibrations. So this is just a representation of a crystal lattice. So everything that has heat vibrates. So we can think of these atoms in our crystal lattice as being on springs, and since they have heat, they can vibrate. And from these vibrations, we get waves called phonons. These are some of the things that we measure in IR spectra, or Raman spectroscopy. So now let's get on to Cooper pairs and electron-phonon coupling. This would be a great Halloween outfit, at least I think so. If one goes to electron, one goes to phonon. No one liked it, so I didn't go for that as Halloween. So BCS theory is predicated on the formation of Cooper pairs. When we have Cooper pairs, we have superconductivity. So what we have here is we have a phonon wavelength, we have two electrons, and we have positive cations in our lattice. So what's happening is our positive charges in our metal, this could be any metal, you can put lead in there for example, they attract this negatively charged electron, pushing it this way. The magnitude at which they're attracting it is related to the phonon amplitude right here. Conversely over here, since we have negative amplitude, the positive electrons are bringing this, the positive cations are bringing this electron over here. So we have two electrons, they have to abide by Pauli's exclusion principle. One has to be spin up, one has to be spin down. And the distance between the two is related to the phonon wavelength. What's interesting about these two, about Cooper pairs, is we have two fermions, and our Cooper pairs are bosons. So what that means is we can have a bunch of bosons existing in low energy levels. That's why we can get such low critical temperatures for our superconductors. So our critical temperature is related to our distance between our two electrons in our Cooper pairs, called coherence length. It's this Xi Greek symbol right here. So the lower our critical temperature, the farther apart our electrons in our Cooper pairs are going to be. And this delta sub naught right here is called our energy gap, not to be confused with band gap. So this delta sub naught, this energy gap, is the amount of energy it would take to break our Cooper pairs apart, or electrons apart in our Cooper pairs. So if they're really far apart, it wouldn't take that much energy to break it apart. But if we have a higher critical temperature, right, of lead right here, it has a much smaller coherence length of 90 nanometers. It would take more energy to break it apart. So, of course, my research is on how pressure affects the critical temperature. So what we see is this is a graph of a bunch of research and a bunch of data compiled, put on one graph. And what we see is a trend, a general decrease in critical temperature when we increase our pressure. So if you might look, the axes are kind of funny. So on our y-axis right here, we just have the fraction of our critical temperature. And over here, you might notice that we have this negative delta V over V. So this is the negative change or percent change in our volume. So you might be thinking, why are we measuring a percent change in our volume when we're measuring pressure? We get a lot of non-linearity when we measure purely critical temperature versus pressure. So what's common is that we measure critical temperature versus our volume. The way we convert between the two is what Smith and Chu said, is that they convert the specific metal, they impose a specific pressure on the metal, and they convert that to a specific volume of the lattice structure. They use Bridgman's room temperature compressibility data to do this. And one assumption that they made is that since we're working at such low temperatures, the room temperature compressibility data wouldn't change the compressibility of our different metals. So the point of this paper, if you can read this very shocking title, Will Pressure Destroy Superconductivity? The goal of it was to see at what pressure could we completely suppress our superconducting phase transition, effectively making our critical temperature zero. So what they say, if we assume that these relationships between our critical temperature and pressure keep on going when we increase our pressure, that yes, we can eventually, in fact, completely suppress our superconducting state. So we want to figure out what is exactly happening. Why, if we increase our pressure, are we going to get a decrease in our critical temperature? To do this, we're going to look at two different superconductors, one conventional case, one unconventional case. So let's look at lead for a conventional case. We like lead a lot in superconductivity, not so much in paint or toys, but we like it in our superconductivity. We like it because, one, it has a critical temperature of 7.2. This means that we can use liquid helium to cool it below its critical temperature. Also, we can get lead up to a really, really high purity, 99.999% purity. So a better purity that we have, the better superconductor we have. Because if we have a lot of impurities, we'll have a lot of different competing phonon-electron interactions, electron-electron interactions, and phonon-phonon interactions. So to measure how pressure affects our critical temperature in a theoretical way, we have to use what's called the strong coupling BCS equation. Strong coupling refers to our strong coupling between our electrons and phonons in the formation of Cooper pairs. There is a weak coupling BCS equation that's a lot more simple than this thing, but it only works for aluminum, right, because it has weak electron-phonon coupling. So how are we going to figure out how pressure affects this equation? we're going to play a game called Cancel Out the Variables. So we take this initial equation, we want to look at what variables do we have. So I'll start with this mu star right here. This mu star is Coulombic superpotential, or the repulsive Coulombic forces with electrons in our superconductivity. So what is found is that throughout a variety of pressures, this mu star, this Coulombic superpotential, remains relatively constant at 0.1. Also, through all of our different metals, right, we get a 0.1, so that's really interesting. So we can make the assumption that our mu star is going to remain relatively constant at 0.1. So now we're going to look at this lambda term right here. Lambda isn't wavelength. Lambda is what's called our coupling constant, or our electron-phonon coupling constant. We can think of it as the total number of electron-phonon coupling that's occurring in our superconductivity. So if we sum this integral, we get these four terms. We get this NEF, I squared, M, and omega squared. So this omega squared is our phonon frequency. This M is just the mass of a metal. This I squared term, it's got a really long, convoluted, complex, technical definition, but really what I squared is how the phonon energy relates to the coupling of electrons and phonons. What we find is that really relatively insignificant changes when we impose pressure. So let's look at this NEF, or the density, electronic density of states of the Fermi energy. So density of states, we can just think of it as a population of electrons around the Fermi energy. Again, insignificant change with pressure. So I think you know where this is going, right? Insignificant when compared to our omega, right? Our phonon frequency. Let's go back to this lambda right here. The way we do this is we have to assume what is called the multiple cutoff Lorentzian model. It's just a big technical definition for manipulating this phonon density of states, or the population of phonons. And we can break it up to both transverse and longitudinal waves for our phonons. So if we think of our crystal lattice, right, we can vibrate a bunch of different ways. We have a bunch of different wavelengths, a bunch of different waves from phonon. So we can break those up into both transverse and longitudinal waves. And using the data by Frank and Keeler, what we see is that if we increase our pressure, we're going to be increasing our phonon frequency. So if we're increasing our phonon frequency, we're going to be decreasing the total amount of coupling that's happening between our electrons and phonons. This is resulting in our negative, what's called pressure coefficient, or a change in critical temperature with respect to pressure. So this was a theoretical approach. So how does this work when compared to experiment? Actually works pretty well. This is just 3 different data from 3 different papers. The Smith and Chu one was from the pressure coefficient earlier. So what this shows is that, yes, our theoretical assumptions that we made, and that if we're only accounting for our change in our phonon frequencies, this is one of the main driving factors in decreasing our critical temperature. So what does all this mean? If we're increasing our pressure, we're going to be increasing our phonon frequency. This means if we're increasing our phonon frequency, we're going to be decreasing our electron-phonon coupling, therefore decreasing the total amount of Cooper pairs that are being formed, therefore decreasing our critical temperature. This is nice.